All right, thank you everyone for coming. This semester we have 4 mathematics students who are graduating and they're here today to present their senior projects. I've had the honor of supervising all of them. They're all on 3 very interesting topics in my opinion. They've all done a fantastic job. So without further ado, I'm going to let Fatima start us off here. Fatima is doing her research on the study of Lie group symmetries and ordinary partial differential equations, which have a non-local and non-linear characteristic. Fatima?
Thank you. Hi everybody. My senior project was about Lie symmetry and differential equations. Let's start. So in solving differential equations, there are no general methods to find exact solutions. We're used to solving ad hoc methods in usually in regular differential equations classes. Nonlinear differential equations are more complicated to solve, but there are still handful of methods for solving them. Riccati equations are an excellent example of nonlinear differential equations. And so an example of a Riccati equation is y prime of t is equal to x squared plus y squared, which is like complicated to solve, but there are still methods to solve this. Functional differential equations appear in a great number of contexts. There are a bunch of applications for that, and then it includes non-local functions and memory structural functions. We will focus on the Lie symmetry method for solving differential equations. So this Lie symmetry analysis used to unify the ad hoc methods for solving differential equations, where it is used when we can so we can transform a first order nonlinear differential equation to a separable equation, which is we can solve. Lie group, so we're gonna transform the first order differential equation to a separable equation. We're gonna use transformation, where they are Lie group, where they are named after Sophus Lie, who laid the foundations of theory of transformations groups. So let's consider a set F as a set of points x, y in R2, and G as a set of points x bar, y bar in R2, and then L is going to be a topological group with a smooth manifold structure, such that we have this x bar and y bar are the transformations. So we're going to map R2 into R2, then the set xy into x bar, y bar, and this mapping is called a one-parameter Lie group with a parameter epsilon, where epsilon is a small parameter, is a small number. So here we're going to focus also on just one parameter Lie group. We're going to solve, so consider this ODE. We're going to solve this ODE using Lie symmetry. We have this ODE, and we want to use the transformation x bar, y bar to transform it into a separable equation. So P is dy dx. If we consider P is dy dx such that P bar is dy bar dx bar, where we can find it using chain rule, then we expand x bar, y bar, P bar. We Taylor expand this in a parameter epsilon, where x, y, and p are the infinitesimals here. So given x, y, and p, we can change variables of the ODE, then to change it to a separable equation. Then x bar, y bar, p bar should satisfy this condition, which is Lie's invariance condition, which is an underdetermined PDE. So basically we're changing this ODE into a separable equation, and then we're changing it to a PDE that we want to solve. Here's an example. So we're going to solve this complicated ODE, which is a class of a Riccati equation. We're going to consider that this ODE is invariant under this Lie group with a parameter epsilon. Then we can find dy bar dx bar using chain rule, and you can check that, and then we get this equation, which looks the same as the original ODE. So if we know how to solve this ODE, we know how to solve this ODE. Then we're gonna here change variables. So when we change variables x to the e to the s and then y to our e to the negative s and plug them in the equation, then we're gonna get a separable equation which we can solve. We just integrate and then we plug in the r and s again in the equation to get the solution in y. Then we apply this Lie symmetry to PDEs. So we we started by the PDE of tx, u, ux, ut, and then u here is going to be u, ux, ut. It can like have any, we can have first or second derivatives, partial derivatives. Then we need to find a Lie group t bar, x bar, u bar where the PDE is invariant under this transformation by a parameter epsilon. Then we're going to expand again here. So same as in ODE, we're going to expand, Taylor expand t bar, x bar, u bar. So we're going to expand just the first order here at and the derivative is going to be at the origin, where the infinitesimals are t, x, and u. Then using chain rule and Cramer's rule, we get two expressions for u bar, t bar, and u bar, x bar. And then we have here big U, t bracket, u, x bracket, where are the differential operators. Then dt and dx are the total differential operators where they are given by these equations, which are partial derivatives expressions. Then we're going to find the Lie's invariance condition. So we're going to consider gamma to be this, and then we can apply this to our PDE, to our original PDE that we have. So then we're going to set this equal to 0, which is our Lie's invariance condition, and then we're going to try to solve this. Then we have to solve this Lie's invariance condition for t, x, and u. After solving this, we're going to consider new variables here. We're going to change variables from txu into rsb. Then we apply this operator again to the equation we get. Then we change variables to get this system of PDE, which is first order linear PDE that we can solve by using method of characteristics. And we can assume here that this is equal to 1 to eliminate one of the variables to make it, to solve it. Then we can solve the system of PDEs to find our S and B. So here's an example of a PDE. Berger's equation. This solution, we can find it using method of characteristics, but then we're going to find the solution using Lie symmetry here. So we're just going to apply the gamma operator to the PDE. We get this equation. Then we have to substitute ut bracket, ux bracket, and then do a bunch of substitutions and calculations to get these two equations. And as you can see, as you can notice here, that this form is similar to Berger's equation. Then we're going to let t be any arbitrary function, and x be this function, and u this form. Then we're going to consider a special case for t, x, and u, and then plug in the PDE system of equations, then solve the system to get our S and V. Then now we're gonna change Berger's equation from local differential PDE to a non-local PDE. So here we have, in Berger's equation we used to have u, ux, but here we have k of u, where k of u is a non-local operator. So using the method of characteristics, we get a non-local ODE. Then with letting u be a solution for the PDE, we get du ds. Then using chain rule, we're going to get x prime of s equal this integral, where we're going to have this PDE, which is a non-local nonlinear PDE, where we're interested to solve this equation. So we're considering delay differential equations. Delay differential equation is a type of functional differential equation, and a special type of retarded differential equation. So here's the delay differential equation. We're gonna we're trying actually to apply this Lie symmetry to this delay differential equation to find a solution for the non-local differential equation. So let P be dy dt such that P bar is f of t bar, y bar, z bar, where z here is y of t minus 1. So this will lead to an infinite system of ordinary delay equations. So it's gonna give us a linear differential equations, which is better. So here we're gonna consider a special case with a one-step function. So let's consider that y of t e to the lambda t is a solution of the delay differential equation, and then we're gonna y prime t is gonna be this. Then we can do similarly for y of t minus 1, same thing. Then we're gonna get out of these two lambda e to the lambda t, e to the lambda t, e to the minus lambda. We're gonna get this. Then the solution of the equation will be y of t c e to the wt, where wt is the Lambert function, which is the inverse of lambda e to the lambda. So we're gonna seek roots for this equation where they're gonna be complex roots. So let lambda be a plus ib and seek solutions of this equation. Then using Euler's formula, we can get this equation, and then the solution will be the system of equation, which have infinite many solutions, but a potential general solution here will be this solution including Dirichlet series with complex coefficients. Then we're going to Taylor expand the one-step function. So we're just doing Taylor series here. Then we get, so using this, we get this equation. Then this implies that our delay differential equation can be written as the Taylor expansion in D, where D here is the derivative operator, which is dy. So consider the set of polynomials, okay, let's say. So dy e to the negative d y of t, where here e to the d dy, as I said, d is the derivative operator, e to the d is just the Taylor expansion of e, so it looks similar to this one, but with positive signs. Then our problem will have this solution, e to the t, e to the negative d, and we can Taylor expand that. Then e to the negative dy of 0. Then if we multiply it by t, we're gonna get this. Then furthermore, we have, so if we have e to the negative d, e to the negative, we're gonna get this Taylor expansion, and we can do the same for nth term. So from this we can see that the solution dy of t is e to the dy of t, or equivalently e dy, would be equivalent to finding the operator d such that d is e to the log d. So as we know, like from let's say from any function, so if we have like x e to the log x, it's equal, but here we have d as a derivative operator, where, such that d log d commute with this property, they should be equal to 0, then we can write our equation as e to the d plus log dy. Now we're gonna define log d as a Fourier multiplier. So consider a Fourier expansion of a 2 pi periodic function, and then the Fourier coefficients are this integral, and then we define a Fourier multiplier operator by this. So this is the Fourier multiplier, and then we can see that d to the k will have in to the k term, and then it also follows that translation is a Fourier multiplier with symbol e to the in. E to the minus d will give us this series. So this equation in Fourier series would have, so we're gonna have this solution which has no 2 pi periodic functions. Indeed, here e to the d dy, and we're gonna have this series y hat of n, e to the in, e to the inx, and then we can get this, where if we want to solve it, as we said, we have no 2 pi periodic solutions. If we consider here pi over 2, negative pi over 2, we get this solution with sine and cosine, a periodic solution. Then if we substitute n and minus 1, and 1 minus 1, we get this periodic function. So here, which occurs in the fact that cosine t is a solution of this shifted equation. Now, since we can do this, we could define, so e to the d is going to be e to the in, and then we can define log d to be log in. And then using the fact that we have L in here, so this is going to be the logarithm of a derivative will involve Hilbert transform, where Hilbert transform is a singular integral operator of a 2 pi periodic function, f of x. And then the Hilbert transform will be minus I sine of n of the Fourier of the function here. And then where sine n is alternating between 1 and minus 1, which follows that log d will become this, so this function including the Hilbert transform. And here to exclude 0 from here, we're gonna shift here by I, where I here is the identity. So to exclude 0. So while this powerful method was interesting, we would like to apply this method to the non-local nonlinear differential equation, which is here delay differential equation. So we tried different approaches to solve this delay differential equation, and we will continue to investigate to try to find a solution for this. Some reference. And then questions.
Are there any questions for Fatima?
A very simple question here. Can you go back to your 18?
Yes.
So is that log there? It's
Yes.
a special log, right?
Yes.
Which is natural log.
Yeah, natural log. Yeah.
Okay.
It's yeah.
Because I saw that you are using later on you are using.
Yeah, we're using just natural log. Yeah.
Okay.
Yeah.
So that's something acceptable usually in math, like going from one to the other without putting the base.
Yeah, I think so.
It doesn't matter so much in this context. We're just trying to define an operator that has this property that can use with the derivative operator.
So it's implied once
It's
you put it
implied,
in the
yeah.
log.
If I can find one that has the lead bracket being 0, we got all of them basically. So yeah.
So when you go to the next slide, when you have there e to the I and x, those are all three like I square root of minus 1, n is a variable, x is a variable. Cool, thank you very much.
You're welcome. Any more questions? Yes.
Going back to slide 17 again, just the same comment here. Which one was 18?
18?
Right here. So D again equals E, like LMD. D has to be positive, right? Otherwise this will not be true.
D here is the derivative.
So D is the derivative now.
Yeah, so it's not like, yeah, so here we're not considering like a sign for D basically, so D is just like the derivative of the function, the derivative operator, yeah.
In general, I think it can be anything that goes in the argument can be complex value as well.
Yeah.
So,
Right, in this case
It's a complex version of the natural
right,
the extended version.
right. Some sort of counter continuation or something. So that logarithm there, is it like defined by the usual log series or?
By the what? Natural log?
So what does that mean to say the log D? Like,
We need to construct an operator that behaves like this.
right.
It's really a kind of pseudo differential operator. It's not ordinary log, right?
Yeah. So
But we want it to behave like a log.
Right.
That's what we call a log. Other questions? Well, let's thank Fatima again.
Thank you.
All right, our next talk is by Derek Seidel, who's going to talk about the analysis of the existence of NBA superteam via particle fragmentation coagulation models. Derek, you can take it away.
I wonder if Derek knows anything about basketball.
Yep, so so as Dr. Debkowski said, I did my project on NBA super teams and basically looking at how superstars move throughout the NBA. So just to give a background on the issue at hand. So like a super team it's a common term nowadays. It's something that you hear to describe a team that has multiple top tier players, multiple stars on one team. That typically it can be constructed in any fashion, whether through the draft or free agency or trades. It's become more common recently for these super teams to pop up. Largely because there's a lot of speculation as to why, but a lot more movement is occurring through free agency with players. The loyalty has gone down, and they're more, people attribute it to them being closer off the court and stuff, so they tend to want to play with each other. So you'll see teams leave, and there's less, you're less likely to stay in one place. And so with that, there's become a lot of these groupings of superstars that come together and then fall apart quickly, so that's kind of what we're looking at. In order to look at the problem, we have to obviously define what a star is. So to do that, we chose it as the top 30 players. You could choose any number you wanted for your definition, but we used, for this one we'll get into it, but we end up using like there's rankings that are released every year that rank the players. So yeah, that is the background about the problem. So in order to look at it, we chose to break down the league into concentrations of super teams of each, or not of super teams, sorry, of each star of each team. So what percentage of the league has 0 stars? What percentage of the teams have 1, 2, or 3 stars? So we can look at it that way. And that is represented, as you can see here, by a big C, with C1 being the concentration of 1-star teams. And we only went up to 3 stars per team, because in order to have more than that, the cap restricts teams from, in general, from having more than 3. Occasionally you'll see a 4-star team pop up, and then it's even more rare. So then with that, we chose to look at the league based on these stars and where they go. So how they move from one team to another, and how that changes the concentrations of the teams in the league. So that is done through these coagulation and fragmentation terms, which is A and B, which is shown better here. So A in this case represents, an AIJ here would be a team with I stars and a team with J stars, and them joining together in one team with I plus J stars. So for example, if it was A11, there'd be 2 1-star teams, and one of the stars from one of the teams went to the other team, and now you have a 2-star team and a 0-star team. And then BIJ is the opposite of that, which is if you had a 2-star team, and it would B11 would be a 2-star team breaking into 2 1-star teams. So I plus J becomes the 1-1. So that's like how we looked at it. Here's the data that I gathered for the league over the past 5, or I think it was about 5 years, which is as long as ESPN and Sports Illustrated post their data for, they rank the players every preseason. They rank 1 through 500 in the league. So this is the concentrations we gathered. As you can see, it varies from sources like Sports Illustrated and ESPN don't have it exactly the same, because obviously it's up to people's opinions. So there's a lot of different ways you can come up with rankings for the actual players, but this is what we used to come up with the data. So in order to look at the movement and the coagulation and fragmentation that I mentioned through those terms, we compared it to the Becker-During equations, which is a system of an infinite system of differential equations that is used to model how particles join together and fall apart, especially during like changes of state. the biggest example that helped me understand it kind of is if you had ice cream and you've had it frozen ice cream and you let it sit out and it melted, and then when you refreeze it, like how it joins back together, how they group together when it refreezes is the best way for me to understand it. But yeah, so we have these equations here that represent the concentrations. So C1 here is the monomer concentration, which is kind of it's the most important concentration in the Becker-Dirichlet. It has a different representation than the rest, and it kind of has a sort of tends to come back to that, back to the C1. Yeah, and so the FJ breaks down into the AJ and the A and B, which is like what I mentioned previously. So to look at this, we applied this to the MBA and then try and find an equilibrium. So in this case, I can actually write it on the board for this. Like if you were to find an equilibrium here, which is kind of the same pattern we used with it. So you have all your CJs. If you had the first, or the C1 is equal to C1 dot is equal to this, and then all of them going on from there. And then you have your C2 is going to be C1 minus, F1 minus F2. And C3 is going to be F2 minus F3, and so on. So if you want to find the equilibrium, you set these equal to 0, all of these equal to 0. And what you'll find is that it'll be F1 equals F2, and then F2 has to equal F3, and so on. So they all have to equal each other in the end. So then if you set this equation equal to 0 and all the F's equal each other, the only way you can do that is you have to have the F's have to equal 0. So then you can go back to the F equation for the Fj, which is equal to AJC I C1. And what you'll find then is that you'll find that if it's equal to 0, you can end up with the relationship of them equaling each other. And then you can put the C's all on one side, or the CJ plus 1's on the same side. And then by plugging in 1, 2, and 3, you can find the what you'll have for the equilibrium concentration for each concentration. So just for an example, just to do 1 and 2, which will apply to ours, it would be A1 C1 over maybe we're doing this wrong. Yeah, that would be 2, and then C2 over C1. So you have these equations that will go on, and then it will apply here. We basically were able to find these. That came out the same as that. My handwriting is terrible, sorry. But yeah, so when we apply to this, which is, we took that and applied it to the MDA, which it's no longer an infinite series now. We chopped it off after 3, which changes the dynamics of it, which was interesting, but the equilibrium state remains similar or the same for those values. So yeah, so here we have the concentrate, like the 1 star, or how the 1 star teams change, how the 2 star teams change, how the 3 star teams change based on all the different terms from before. Like, so this is again the 2 star team, or 2 star team breaking into 1 star teams, and so on, how they relate to one another. So with that, and following this sort of strategy, we were able to come up with an equilibrium curve for the league, for the model. So, and here's the U, and then the U squared, U to the 3rd, that we found. So this is the way it kind of comes out. And so then with this equation here, this is like kind of the constraint on this the league. So you're with K being the number of stars, this will always have to remain true for the league to remain safe. So if you set this league at 30 stars, you're always going to have this be true, so that is always still 30 stars. And because of this, since if you take the derivative of this, obviously since k is a constant, it'll be 0. So it's not changing. So it turns into planar dynamics rather than like surface dynamics or whatever. So that makes it interesting. But also, so when we choose, if you go back to here, when we choose our values for all the B's and A's, and then whatever your original concentrations of C1, C2, and C3 are, it'll stay on that plane, and that plane will intersect our equilibrium curve that we found, which is right here. So this kind of displays that. So you have the blue line here is the equilibrium curve that we have in this example, which is with one given set of the A and B terms. And then at any of these points is out here is where the starting concentration we chose, and it always, after this was over, I think 5,000 with the time, and it always comes in to the equilibrium curve over time. So that through this we realized, oh, I just hit the cord, that it appears to be stable. So, it appears to be a stable equilibrium at the curve. So that's what we're hoping to then prove analytically. So in order to do that, we looked into Lyapunov functions. So a basic example of a Lyapunov function is for this spring equation with friction set up here with the at the top, and then if you choose this as your Lyapunov function, and you can derive it and find this equation here, and then as you then plug back in your values up here into this equation, and then you'll end up with a negative 2y squared left over, which with it being less than 0 means that it is stable at that point, because x squared plus y squared is what do you call it? It goes into the minimum is at the origin, so everything is heading towards that equilibrium at the origin in this case. So that's kind of what we're trying to apply to this MBA model. And for the Becker-Düring equation, the infinite series, there is a known Lyapunov function, which is here. But we chose to not look at that one originally because without the infinite series, we didn't feel that would be the best way to start. So we chose to try this equation, which is with like a three-dimensional version of the last Lyapunov function we found. So then we have expanded that into all this mess here. And basically, in order to prove that this was a Lyapunov function, we have to find a value for this little a, little b, little c that are all positive, and the equation will come out negative. So we worked through this quite a bit. We think there might be a way to do it, but we haven't found it yet. We also think that if we somehow find something between all of this and the function here for that full Becker-Düring equation, we could find a Lyapunov function that proves the stability. So that is it.
All right, thank you, Eric. Do you have any questions?
So what is stability in your case? Like, what does it actually mean? Not the math. I understand
on the math? Or
not the math.
Oh,
like
so,
the system
oh yeah, I guess I didn't really get into that, but, so what that would imply would be that if you had, if we were able to find, so the tricky part would be to find your correct values for all the, for these here, like finding your A11, B1, like all those values would be very difficult, but we could try and do so with the data that we have. And then if you were able to set those, and then whatever concentration you were at, you could try and predict where it was going based off of our model there. And the equilibrium in that sense would mean the league would reach a point where you'd have the same number of you'd always have the same number of 3-star teams, the same number of 2-star teams, the same number of 1-star teams. It wouldn't necessarily always be the same. That's like with using concentrations, it could be different teams. But that's kind of what we were looking to find.
And my second question is, can you go back to your graph? Could you explain the axis a little bit and what makes it stable? Not
This right,
this,
the
yeah, the MATLAB.
So the actually, oh yeah, this is, I believe this one here is the C1. This one is C2, and this one is C3.
Okay, and what does it imply that the system is stable? Because your conclusion there, it says, which supports the system being stable.
Because I think my understanding is like, so we basically chose the parameters of C1, C2, and C3 to be out here, like at this point, and then after we ran it over time, it reaches back to this curve. This is the curve that, this equation here, we entered this in, for the values of C1, C2, and C3, and you get this curve right here. And then if you run we just ran simulations using MATLAB and starting it out here, and it always, over time, it ended up like back to this point through the, I don't know if I'm doing the best job explaining it, but it always has this cane shape and ends up back on the curve or near it. And when we looked at like it really close to that point, it didn't always get there even after 5,000, like going 5,000 tries through it. So
do you remember in physics we used to have a curve, and wherever you take an object and you're moving away from the curve, it always falls down to the bottom.
Yeah.
So that's the stable equilibrium. So it seems that that's what you're trying to run. Okay. Thanks.
Yeah, that's
very
right.
nice.
So I have a question about the curve. So go back to your previous slide. Is that C1 plus 2C2 plus 3C3 plus K, how is that related to the curve that you have in your next slide, the equilibrium curve? Is there a relationship? Because this is a linear relationship in C1, C2, and C3, but that one is clearly not a linear relationship. So I'm wondering.
So we used this to find, this was the equation we used to find the equilibrium curve, I think is the way, yeah, so we used these here, by applying this we were able to find these values, and then I think, if I remember correct, I should have put the actual equation of the curve on here.
So that linear relationship, each one of those curves is going through a particular choice of that plane, right? So there's planar dynamics. So the question becomes is, as I slice with this plane, with different values of k, I get these different curves, right? And that's helping us with it. It's like a conservation of mass condition, basically, right? I have the number of stars times the concentration, so that should be a mass.
So that k is what is bringing some sort of nonlinearity.
Yeah, it's actually quite complicated.
Quick question, are your like aij's and bij's constants?
Yes, and you can, like they're constant within the
They
equation.
don't change
Over time, no.
Over time steps?
No.
Okay, so if you have a cutoff at like C3 where you don't have any more than a concentration of 3 players on one team, and you also have coefficients of teams splitting up being constant, those are the two conditions that will force you towards an equilibrium condition, right? Is that right? Because you have a fixed number of players, you always have a term that takes 3-star teams and changes them into 2-star teams. And that constant probably is a different size than the one that takes 2-star teams and combines 3-star teams. So the combination of those two constraints will force you into an equilibrium situation. Like you'll never have here's all teams are 3-star teams and all the rest of the teams are 0-star teams because those coefficients are not 0.
Yeah, that seems to make sense. Yeah, I hadn't thought of it that way, but yeah, that's actually a good way of looking at it, I think.
Other questions for Derek? All right, let's thank him again. And to wrap things up, we have Shane and Marshall, who are going to discuss how we can use optimal control in Hamiltonian dynamics to model Twitter mentions and the evolution of mentions on Twitter for musical artists. So Shane and Marshall, take it away.
All right, so me and Shane are both very interested in music, and when we were trying to consider some kind of research project, we obviously had to introduce something that we really liked because it made it much more interesting. So we were looking at the optimal times to release music and how that would affect your mentions on Twitter. We basically assumed that if you got a ton of mentions, you're pretty popular and you're doing well. So that's our basic assumption throughout this. You want to optimize your mentions. And we look at this, we're considering what kind of promotions the artist uses, the popularity of the artist and the timing of the release. Overall, our goal is to minimize your cost. We don't want people to spend as much of their budget as possible, and we want to maximize your tweets.
Yes, so the way we wanted to approach this problem was through optimal control, which is a special type of optimization that hasn't really been applied to this system. To kind of give an overview of optimal control, we are trying to solve the maximization problem up there, where R is sort of like a running total, and G is sort of a terminal value. You kind of add those two together, and that's like a final score for your optimization. And we're trying to get the maximum score over all U's, which are functions that range between 0 and 1. And then x dot equals f of x of t. U of t is our sort of our control dynamic, how the system will change. And we can solve this problem with the Euler-Lagrange equations. So we'll define the control Hamiltonian first as h of x, p, and u equals p times f of x and u plus r of x and u. Those come from what's above there. They're the same expressions for the dynamics. And the Pontryagin maximum principle gives us a costate called p of t, such that if our optimal controller is u star, our Hamiltonian flow is expressed through the gradient of our Hamiltonian. So we can get our x dot star and our p dot star. And then the transversality condition, p star equals gradient of g at x star at the terminal time, allows us to uniquely solve this system. So then, first thing we applied this to was a single music release on social media. So if an artist releases just one song on social media, we're looking at what they can do to promote it best. So let m of t be the number of mentions that an artist accumulates on Twitter up to time t. U of t is an advertising package that the artist purchases from a firm at time t. That ranges between 0 and 1, and you can sort of think of it as the intensity of the ad campaign that they're purchasing. If they're hiring a firm to use all their resources, or if they're hiring the firm to use only a few resources. And then B is just the cost per Twitter mention that the firm will charge. A lot of these promotion campaigns that we looked into, they charged you for how many tweets that you accumulate during the time that you're using their services. So if we look at the differential number of mentions m over each time step, partition the time interval into m time steps, we can create a Riemann sum and turn it into an integral for the cost, which is b times the integral of u to capital T, m dot times u dt. Yeah, so during a promotion campaign, from the data that we collected and looked at, we saw that mentions of an artist will ramp up dramatically, but when there's no promotion campaign, they'll grow at a small constant rate. So our control dynamics are m prime of t equals epsilon plus u of t times m of t. Epsilon is sort of the constant small growth rate that happens. This means that no matter what, the artist's Twitter followers will tweet about the artist a little bit at a linear rate at all times. You can kind of see this on the graph. If you look here and up here, there's sort of a linear growth rate before the release date. So that comes from epsilon. Then when we turn up our promotion u up to 1, we get this exponential growth, which kind of cancels out the epsilon because it's a lot smaller. And yeah, this graph comes from actual Twitter data about Justin Timberlake after he released his last album and performed at the Super Bowl. So this is like the best possible case for promotion when your Twitter mentions just explode like that. For this problem, our control Hamiltonian is expressed like that. When p is less than 2b or otherwise u is less than 1, we get epsilon plus mu times p minus b u squared m. Then when p is greater than or equal to 2b or otherwise u is greater than or equal to 1, then we get epsilon plus m times p minus bm. then the Pontryagin maximum principle tells us that u equals p over 2b, and that lets us simplify the Hamiltonian, and we can find the system. Here we solve for p star of t, but once we have p star of t, we can get u star of t, which is our optimal solution for our promotion. And we can show you a graph of what that looks like. So u star of t will equal 1 up to a certain time, which is capital T minus 4b minus 2. And then it will turn into this sort of decaying curve, 2 over 4b minus t. So this is a specific case where b equals 1, so it's like the cost per tweet is 1 and total time is 5. What this showed us is that basically you spend as much of your money as you possibly can until a certain point. Then you're allowed to ramp it down in this shape to both save money and optimize how many tweets you'll still get when you're spending less money on the promotion. And then you'll stay at 1/2 as long as you can, and then eventually just stop promoting. So yeah, it ramps down from 1 to 1/2.
From there, our next question, now that we figured out the best way to use your money when you're dealing with one release, is to figure out how the best way to use your money and how to plan things out when you have multiple releases. So we think of it as a sequence. You have multiple time intervals from T1 to Tn. Obviously, Tn is greater than T1 as you're moving along. We also have that ambient growth rate, just like we mentioned before, which increases as you go on, because we're assuming that once you have that exponential growth, you're no longer going to increase at the same ambient growth rate. You're going to have more interest in you. I mean, otherwise a little artist would never get bigger. You would just have the same ambient growth rate forever. We restrict our release time so that you basically have this period between your release time and delta. In a later case, we basically just choose an arbitrary delta to show something, but that would be determined based on the artist. Like I said, what we really want to know is when we can choose these release times so that we can maximize the number of your terminal mentions. So, what we're looking at here up in the top, we're basically, this is a case where you have two releases. You have your initial ambient growth, and then you have your exponential growth based on your time interval delta. And then your next ambient growth rate is adjusted based on your exponential growth from the previous term. And then that continues on where you have your exponential growth again for your second release, and then you have your ambient growth that's a little bit either raised or, no, only raised based on what happened previously. We're also saying here that we eventually decided that you need to push these releases as close together as you can. You want those exponential growths to basically be one after another, because if you minimize the difference between your initial epsilon, your initial ambient growth rate, and your next ambient growth rate, you're going to minimize the amount of decay in your final Twitter mentions. So looking at a graph like this, that's what we would want it to look like as far as your release timing and mentions go. So you push them as close as you can together, you get those exponential increases one after another, and your final ambient growth rate, basically what you're going to be riding on after all your releases are done, is going to be as great as possible. So this is more of a long-term solution versus a short-term growth solution. There are reasons that artists can't do this. This isn't always practical. First off, you can't determine when your exponential growth ends. There's no exact way to know the way it goes without using math like this. That's why people don't do it currently. We don't know the quality of the music. So obviously there are some people who release songs who are not amazing, and there are some people who release songs that are amazing, and that's all, you know, based on opinion, but that would determine how much they grow. We also know that in this case, you may oversaturate the market. You know, when people release one song after another, people stop caring a little bit because it's a little bit too much at once. There's no excitement to it. There's not that one big release that gets you interested. In the future, what we really want to look at is other types of growth rates. So in here we show that there was an exponential growth rate because that was the most common case in their tweets. When you had that big advertising boom, you had that exponential growth rate in tweets. We also want to see what the effect of the sentiment is behind your social media interactions. So right now we're looking at volume of tweets, and that's under the assumption that any buzz is good buzz. So, I mean, yes, even bad buzz gets people interested. So you see a tweet that says an album sucks or a song sucks, you're still going to listen to it to see how it goes. but it's not going to have the same long-lasting effect. It's not going to have the same positive effect as someone who says it's amazing. In the same situation, we want to know, like, if a big artist says something good about someone, does that have an insane amount of good pressure? Does it have, you know, something similar to an average person? We also want to know how the dynamics change when multiple artists collaborate. So in the case where you have two large artists, what would happen? If you have a small artist and a large artist, like if a nobody collaborated with Beyonce, it's obviously going to have a big boost in the lesser known artists' mentions. Overall, we do want to thank Next Big Sound and Twitter for letting us use their APIs. That's how we gather our mentions, our Twitter data. And we also want to thank Dr. Nepkowski for all of his help throughout this. Are there any questions? Yeah, it's so automatic.
Is that Beyonce there?
That was, yes, Beyonce and Ed Sheeran. Two superstars.
So when you studied these, do you like, so for instance, Justin Timberlake or somebody, did you go back to where their career started, or like how do you, because...
No, recent. We looked at our recent set of data because realistically looking from the very start to now, I guess in the scope of things, if you're trying to investigate how a starting artist would grow, you could do something like that.
That's what I was wondering.
Okay, yes.
Did you compare between somebody who's a big shot versus somebody who's starting off?
We did compare people like that, but we didn't investigate large stars from the beginning. We were more worried about, like, if a large star released something right now, what would happen?
Justin Timberlake also has been around longer than Twitter, so.
Yeah, so that would be,
So,
yeah.
but we did find that, like, really unknown artists, their epsilon, like their linear growth rate can often be 0. Like, there's no one tweeting about them unless they try to get people to tweet about them. So it's what you'd expect.
That's actually why we had to switch the way we were originally analyzing Google Trends data. So you have this unpopular artist, but they have one person who really likes them talking about him every day. So they have a Google Trends of 100 all the time, and you'd think like, oh, obviously, no, they're not popular. They just, their mom likes them a lot.
What about somebody who was like long time, like for instance Beatles? I'm sure people talk about Beatles on Twitter. Right?
I'm not sure. I don't think we've considered that because we don't know what would happen if they, you know, if any living Beatles would release something under that name. I guess that would be something.
Referencing previous songs.
Oh, like looking at their past data?
Right.
That would definitely be something to investigate because they were around before Twitter, so you'd want to know.
Way before Twitter.
We wouldn't be able to use mentions, obviously, so.
For their ambient rate of being referenced, whether that's comparable to some of the, you know, either beginning stars or somebody that's, you know, already popular. I don't know if that can tell you anything more interesting, but something to think of.
Yeah, we also predict that ambient growth rate will decay over time if the artist doesn't do anything, but since we're not looking at that right now, we don't have to consider that.
Now watch how you make this public. You're going to be fired by some politician.
Yeah, one of the problems.
We were just saying to people, if you want to be a pop star, we can test this out. We need a test subject. You've got to have at least one follower, though.
And some voice.
Yeah.
All right, let's thank Shane Marshall again. I appreciate everyone coming. Hopefully you enjoyed your time here. So, and well done to all the seniors again. We're very proud of you guys. So, well done.
Good job.